I will just shortly introduce the topic of the second part of the session. So Javier Novo Rodríguez is from Appentra, the company that we started a few interactions and discussions recently on, especially on the tool that Javier will be presenting today, Parallel tool, which allows you to analyze your code, looking at performance improvements, but also also looking at better developing code development practices for your codes, and showing you some recommendations on how your codes can be fixed. And today session will be organized in a, I believe, short presentation, but also a live demo. Javier, again, thank you so much for joining, and the stage is yours.
Yeah, thank you very much. Okay. Let me know if you have any trouble hearing or seeing. I'm sharing my screen right now. So hopefully you're seeing now my slides. Okay, yes. So as you said, we will be presenting today the Parallelware Analyzer tool from Appentra. It's the first static code analyzer specializing in performance. So this is the agenda for the hour that we have. So we are right now covering the welcome. I'm starting the Parallelware Analyzer presentation. I will try to keep this very brief and try to use most of the time that we have for live demos. So what I will be showing is how you can install and set up Analyzer, then how you can get quick started using the matrix multiplication example that comes with Parallelware Analyzer. Show another more advanced example of the Canny edge detection, which we will be using to provide a hybrid multi-threading and SIMD parallelization, and then some other advanced topics such as how to use a configuration file, how to integrate with CMake to use the information from a build to improve the analysis, how to create cross-file analysis, so when you have multiple files that should be analyzed together. And after that, hopefully we have some time for questions if there are any. So let's just start by giving you some numbers of what you can achieve with Parallelware Analyzer. So for different source codes from classic mathematics problems such as pi computation, the Coulomb, or matrix multiplication, here you have some interesting numbers on what kind of speedups you can achieve both on the GPU and on the CPU. So you can see here, for instance, for the NASPAR benchmarks from NASA, we can achieve up to a 20x speedup and over 100 for GPU. So there is a lot of performance to get from current hardware. This is something that you already know. And the idea is that Parallelware Analyzer helps you unlock that performance. So for instance, in the case of the Canny example, which is an image processing algorithm that we will be using in the demo and that performs an edge highlighting and edge detection of an image. In Intel AVX 500 processors, we could achieve even almost 3x speed up. And this is performing some really simple optimizations that we will see later with Parallelware Analyzer. So depending on whenever your code is more or less hardware friendly, you have to change it or perform some code refactorings that Parallelware Analyzer can help you with. And or if your example is very hardware friendly, it can easily be, for instance, parallelized to improve performance. Then in just a couple of steps, you can already achieve this speed up. Like I said, we will be seeing this in the demo. You see these numbers here are for AMD, and the results are pretty similar in this case. So what are the challenges of software performance optimization, which is the area where Parallelware Analyzer can help? So as you already know, this is a very complex area, and the development and maintenance of good C, C++, and Fortran code is very challenging. When developers, either professional or non-professional, such as scientists that are interested in running their science, need to develop, and they need to get the last bit of performance out of their code. This is a very complex area that many times they are not prepared to tackle. So we want to help with that. And it is very hard to write code that is aware of all the possibilities of the hardware. Also, this is a very fast-moving area, and it's hard to keep up with the latest advancements in hardware. This applies for the software stack. Okay, so when you're looking for performance optimization, you have different areas. You have optimizations that come from the performance, such as using the latest vectorization capabilities of your software. You can use multi-threading. Of course, you can offload to GPUs if you have the hardware available. You can do performance optimizations in memory, such as improving the data locality, or over the network when you have communication, for instance, to the GPU, or even inter-node in an MPI environment. So overall, the parallelism is the key for performance optimization in model computations. And like I said before, parallelism is very hard. Particularly when you have parallel hardware, you can introduce parallel bugs, for instance, data races that are very difficult to find and fix. The bugging is particularly hard, and addressing this is key. Having the right tools to address these problems is key. So we propose one approach with Parallelware Analyzer, which is our solution to this, based on two pillars. The first pillar is a catalog of recommendations, defects, remarks, and opportunities. We want to work with the community. We have been doing this for a while to establish a set of rules, a set of guidelines that we can check over the code and verify that your code is compliant to the best practices of performance, particularly in the field of parallelization. So we have this set of recommendations that will tell you, okay, you should look into this. Probably here you are not looking, not following a best practice, and you should try to fix this. More important are defects, which is something that is already wrong. These are bugs that should be fixed right away. For instance, data race, because you are incorrectly sharing some variable that should be private to one of your threads, for instance. Remarks provide you some hints on how to improve the uses of tools, or how to get tools to get some better code coverage, for instance. And opportunities give you places in the source code where you can act to, for instance, implement multi-threading parallelization, to name just one. So here you have just some of the current defects recommendations, remarks, and opportunities. So for instance, here you can see some good practice, like declare explicitly the OpenMP data scoping for all your variables when you are using OpenMP. Or you have some, like I said before, some invalid OpenMP multi-threading data scoping. This is an example of a defect. This is wrong. This is a data race in your code, and it may be expressing itself already in the form of a bug, or maybe, and this is the trick with data races, it can appear sometime later in the future and be very hard to debug. So it depends on the exact algorithm that you are implementing in parallel. Okay, so the second pillar is, of course, our tool, which is based in the Parallelware artificial intelligence engine, the static code analysis engine, which is the first static code analysis specializing in performance. So the analyzer product is a set of command line tools. At the moment, these 4 tools that you can see here on the upper side of the graphic. It's PW Report, PW Loops, PW Vertex, and PW Trainer. We will be seeing a very quick glimpse of them in just a moment, and later in the demo we will be seeing what they consist on. And these tools rely on a library which is also available as an API. That's what we consume internally, and that what is available to third parties to other license and use. And that library implements the Parallelware core engine, which is essentially the static code analysis technology that relies on LLVM for some of the language support, such as Clang and Flang. Okay, so based on these 2 pillars is what we offer with Parallelware Analyzer. So there are multiple benefits. For instance, you can deliver fast applications for low power multi-core processor. You can save a lot of costs in your software development cycle, and also in the cloud computing. So there are many features that are offered by Parallelware Analyzer. The central concept is this performance optimization report that you will see later in detail, that follows the structure of your source code and provides you with actionable insights, things that you can act upon for each one of your loops or functions. So you will be seeing that you don't need to execute the code. This is a static code analysis, not dynamic analysis. So we just scan the code. We provide you a list of human readable, actionable recommendations. We validate against this open catalog that I introduced, so the best practices in industry, and it also provides good integration with tools such as CMake. You can either show the results in text format friendly to the human, or also in JSON or CSV format, so that you can parse them in your scripts. And we support a variety of target devices such as multi-core CPUs, GPUs, and we will be seeing that in just a while. Okay, so I told you that Analyzer is composed of 4 tools. This is the first tool, PW Reports. It's the entry tool. And when you invoke it for your code, and in this example is this source folder, and we will be seeing this syntax, which is just that you need to provide the location of some header files. What we will provide is a very brief table giving you a summary of what how much of the code we could analyze, how long it took, and with how many actionable items were found for you. So how many relevant things that you can investigate and act upon you get. In this case, I have analyzed the source, the whole source folder, but we could have different rows here if we have different inputs. So in this case, this is the MATMUL example that we will be using in a bit. You have over 100 lines, 1/3 of them were analyzed in just 64 milliseconds, and you have 16 different actions. And these actions can be classified in different types of optimization. So they can either be sequential code optimization, meaning that you don't need to parallelize the code. You can already apply for sequential or serial code some optimizations and get some performance. And that we divide into scalar optimizations, control flow optimizations, and memory optimizations in the case of sequential. So for the later, we have 8 in this case. And then we also have parallel specific optimizations, which correspond to vectorization, multi-threading, and offloading. And here we have 2, 3, and 3 respectively. Okay. One of the things that we try very hard with Analyzer is to make it as friendly to the user as possible. And given that it is, except for one of the tools, as we will be seeing, they are all command line tools, this can be challenging. So what we try always is to provide you with clear suggestions on how to proceed next, not only to apply these actions, how you fix something that is in the code, like saying, add this clause to your OpenMP directive so that you fix this problem, but also how you can invoke the tool and other analysis and different tools that compose the Parallelware Analyzer with different flags. So we try to help you with further uses of the tool. So if you look at one of these suggestions here, it tells you to also use the actions report to find details on all these actionable insights. So that's what I'm showing here in this next slide. So here we are invoking that, and here you have your first glimpse at the structured vectorization, at the structured optimization report that will tell you for its function and loop what issues were found. So for instance, here you have one opportunity for parallelism using SIMD, and here you have some recommendations. So this is the most compact and brief version of the analysis, and you can increase the level of detail using some flags, as we will see later. So this is for PW report. Here you have another example for a bigger code base. So essentially you have the code coverage, which tells you how good the analysis went, but we will be seeing that later. So next we do have the PW loops tool, and this reports a table for each one of the loops in your code with different properties, such as which compute patterns were found. And this is a very important concept in the Parallelware technology, which we classify each of the variables used in your loops into different compute patterns, and based on that information we decide whenever that loop is an opportunity for parallelization. In this case, this loop is an opportunity for vectorization, multi-threading, and offloading. Okay, we will see if we have time more about this. Like I said before, we always give you suggestions, and in this case, you can see how you can use other analysis such as data scoping, which is a very detailed analysis of all the variables in your loop. Code, for instance, which will show you an annotated version of the code, so you can just in your command line see the code with relevant things inlined, and also you can invoke the third tool, PW directives, to parallelize. So this is what this slide is showing, is exactly that, the invocation of PW directives, generating directives of OpenMP for multi-threading, and it is doing that, editing the source code file in place, and this is the result that is telling you, okay, the loop was successfully parallelized using multi-threading, and there is this pattern for the variable C, and this is the resulting code that is added with Parallelware Analyzer. You can either rewrite the original file or even create a new file. Lastly, the fourth tool that composes Parallelware Analyzer is, unlike the others, a graphical user interface, and it's called Parallelware Trainer. So this provides most of the functionality available in the command line, but in a graphical environment. The idea here is that you use this tool to get started in learning how to parallelize, quickly experiment different parallelizations, go back and forth between versions, run the code right from the code editor, and perform quick experimentation. So you won't get so much in-depth analysis as in the command line tools, but it can give you a very nice integrated development environment where you can create different parallelizations, experiment, and learn. So we will report what you see here on the right, parallelization opportunities, also the defects and recommendations. And the idea again is that you create different versions, run them from the code editor, and choose the one that is best for you. So what you do here is click all these circles that are the opportunities in the code, and then you are presented with different options that are analogous to those that the PW directives can do in the command line. So for instance, here you can see that you can parallelize a loop from OpenMP or OpenECC using target CPU or GPU devices and different paradigms such as tasking, multi-threading, or flowing. And then you have some other advanced options as well. So, and I'll try to speed up a little bit since we may be running a little bit tight on time. So in Parallelware Analyzer, you have different requirements for your code. So static code analysis is quite complex. There are a lot of challenges to succeed in static code analyzer. So first, when we are analyzing code, you need your code to be analyzable. So this is essentially syntax issues or code completion that that we require. So for instance, if you require some header files, we need to know the location of those files. This is typically one of the struggles of many people, that they want to analyze the code, but they are missing some files. So we need the code to be complete. So it must be syntactically valid. Let's say that this is equivalent to your code being compilable with an invocation of the compiler. So that's the first requirement. Second, we need to classify your code into compute patterns. This is what I introduced before, this concept of compute patterns that we base our decisions upon. And then based on that information, we decide what is or what is not an opportunity, which loops of your code are good candidates for some parallelization or another, or even for some sequential optimizations. Okay. So again, we could invest a lot of time in going on to the different patterns. So I just want you to get the idea that we have computation patterns such as for all or scalar reduction, memory patterns, which are based on what kind of memory access is being used in your program, so based on that information, we can decide if you should try to change the layout of the data or your memory access order to be more efficient. And then we have some flow patterns that relates to how the control flow in your program behaves and how one part of the code flows into another. So this is some of the different parallelization strategies that we have implemented. We have different ways to privatize variables either implicitly using built-in reductions if your code is performing a reduction, or even atomic. So we have different degrees of support, but I will be skipping this. Again, we have 4 primary types of performance optimizations. You saw this before in the classification that PW report us in the table in 6 categories. So sequential optimizations, we further divide this into 3 categories: scalar, control flow, and memory. And then you have vectorization, multithreading, and offloading. And you have a set of actionable items for each one of these categories. So you can also look from these perspectives. So these are some examples extracted from our website of the catalog for defects and recommendations. You can see here the URL that we use, and then we also provide some code example and the relevance, some context of the tool. So for instance, here we are highlighting that you are performing some inefficient column major access in C, C++, and that by doing a loop interchange, you can do that in a more memory-friendly way. The same happens when you use an array of structs, and you can use a structs of array. So these are the kind of recommendations or defects in this case that will be presented to you by the tool, and that you can check online in our website for the open catalog of defects and recommendations. Okay, so we have released Parallelware Analyzer version 1.0 just a couple of months ago, and we are about to release this month in December version 1.1. So essentially, Parallelware Analyzer is available for Linux, Windows, and Mac for the Intel architectures. And in the case of the Linux operating system, it is also available for Power and ARM processors. So Parallelware Analyzer requires a license. You can ask for one, and we have a trial period, and we will be happy to provide with more time if you need. And we will be seeing this just in a moment on how to set up Analyzer in your system. So essentially, what you need is to set up an environment variable pointing to your license file. Okay. Then we also gather some anonymous telemetry information. So I want to be very clear on this. This telemetry is just recording what kind of analyses are invoked, but it does not contain any information, of course, not source code, not even compile flags, such as the include directories that I was mentioning before. So that information we don't log, we don't know where the information comes from, and we don't even store the results. So let's say that you run analysis of your code, we don't know which file, we don't know which compiler flags, we don't even know how many actions you got from the tool. So essentially what we are looking here is, okay, the tool PW loops was invoked with this data scoping analysis. And so we get some metrics of which analyses are more used and which are not. In any case, this can be disabled by setting this environment variable. And in some systems, we have found that, for instance, in a supercomputer, that the managers want to know how many usages of analyzer were there. So we introduced this telemetry tag to be able to correlate. Like I said, everything is anonymized. We don't know where it comes from, not even the IP address. So with this telemetry tag, saying, for instance, we could establish this to Pawsey, and we will know which metrics are coming from Pawsey. So that's it. Right now, we are supporting C and C++ code. We are actively working on Fortran, so we hope that this comes out in the next few months, hopefully first quarter of 2022. And then we support, like you saw before, OpenNP and OpenACC directives, as well as compiler-specific SIMD directives for vectorization. And this is supported by the PW directives too. Essentially, how would you would work with Analyzer in your development workflow? So first, typically, you would try to work with some build systems such as CMake or Makefiles to extract the build information. And essentially here we are looking for compile flags like the include directories, or even some macro definitions that are required for your code to be complete, or for some code paths if you have conditional code based on macros to match what you need. You would also need, in some cases, to set up multiple files analysis together. By default, analyzer analyzes each file individually, but you may require to group files for their analysis. And then you could set up third-party tools to integrate messages reported by the tools. And this means that you can parse JSON and CSV output. You can set our tools to output that, and then you can parse that, for instance, in your continuous integration systems to detect that, okay, we have some defects here. We should send an email or some alert to someone so that this defect is fixed right away. For instance, if you do your nightly builds on Jenkins, you could run the tool and just look for defects and raise some red flag somewhere for this to be fixed. In general, we recommend proceeding iteratively and working on your hotspot. You can, for instance, in this scenario I was describing, you may be interested in just detecting if there are defects in your code. Okay, so there you are interested in analyzing all your code. But in some other cases, you're trying to optimize your code. You're trying to improve the performance. So in these cases, it should be better for you to work on your hotspot so you don't get so many information from the tool. And then what you would do is identify your hotspot, run the tool for that hotspot, and see which kind of optimization is being reported to you, what you can do, how you can act on those actionable items that analyzer reports. You should measure your performance, apply some of these actionable hints, and then try again to see what the performance is. If you have a performance increase, if your code is still numerically correct, and just iterate from there. Okay, so this is essentially the idea that is summarized here in this slide. Yes, identify your hotspot, work on that with the Parallelware Analyzer tools, see which optimization are suggested, apply them, check your code again for performance improvements and numerical correctness, and iterate again. So that's for the presentation. If there are any immediate questions, I can try to reply them. Otherwise, we can move to the demos, and I was trying also to allocate some time at the end for questions. But if anyone has any question, please shoot away.
Yep, Javier, I think we have one question in the chat. So Pascal is asking, how well does it the tool suggests task parallelism or check that tasks are thread safe?
Mm-hmm. So the degree of support for tasking right now is in the initial stages. What we can do is generate tasking directives if that's the paradigm that you're interested with the PW directives tool, or either the graphical user interface with trainer. But we are not analyzing task uses at the moment. So we can analyze, for instance, GPU offloading or multi-threading or vectorization, let's say directives, if you're using OpenMP, for instance. But at the moment, we are not able to understand, let's say, the tasking that is already in place. So we cannot help with that at the moment, but it is something that we are working on.
Can I have a quick follow-up question?
Mm-hmm.
Which is, so you mentioned GPU. So there's normally some simple mistakes that could be done where you have maybe a data movement happen all the time between, let's say, GPU directives. So you do an offload, but you're moving the data, and then you do another GPU, and you're off, and it's not all in one data sort of offload. Does it indicate those type of inefficiencies for GPU offloading? If you're doing,
yeah, for instance,
I can see that you could group stuff together within sort of an entire data move, like essentially a data block, right?
Yeah, for instance, one example that comes to my mind is when you are transferring more, let's say, an array. Let's focus on a very simple case. So you are transferring a whole array, and you only need a subset of information. So we try to analyze which data range you are accessing from the array, and we'll tell you, okay, here you are copying the whole array, or you are copying this, let's say, 1,000 elements that are not really required. You only need this, let's say, 500. Okay, so this is something that we look into. Of course, there are many different cases for this that can express in many different, there are many ways in which you can transfer to the GPU. So in some cases we will be able to help, in others we still need to support more cases probably.
Okay, anybody would just show up as normally essentially a recommendation that you think there's an inefficiency here, but you wouldn't be able to. Okay.
Yeah, exactly. You will see a recommendation saying that you are copying more memory than you require, so please act on this, and we will be telling you this array in this particular loop, for instance.
Thanks.
Thanks, Javier. I don't think we have any more questions at this point, so I think you can go ahead.
Okay, so what I will be doing is very briefly show you how to install the tool. So this is pretty easy, and I already introduced it, but let's just do it very fast. So let me know if the font size is too small. So here I have downloaded the tool. So if you apply for a trial, we will be providing you the links to download it. So this is no big deal. And then you would just uncompress it, and you have two options to set up the license. I only named one of them before, which is setting the PWA license path to your whole path where the license is found. If the license is not available, it will complain that, of course, it needs a license. An alternative that you can do is just copy the license to your current folder. But this is a little bit more picky because it should be named as PWA.leak. Okay, it has to have this exact name. Whereas when you are using the license path environment variable, you can name it as you wish. This is very useful if you have multiple installations in your systems. So you centralize the license and you can have different versions that are using the same license. And this is the common scenario in supercomputing environments, in systems that use modules. You have other variables that I can introduce before. So in this case, you have the telemetry tag. In our case, we use it as Appentra, so that we know that all the metrics that are logged come from our system, so that we can skip them. Okay, these are not from customers, so we are not interested in this. And this also shows how you can opt out, disable the telemetry if you were interested. Okay. So essentially, to set up an analyzer, this is what you should be doing. Just put the license file, and then if you want, add the bin directory to your path. So this is it for setting up the analyzer. That is pretty straightforward, I think. In any case, if you have any question, you can just contact us. Okay. So what I will be showing now is okay. This to set up here. Okay, I want to show you the code that we will be using, which is MATMUL. It comes here in the examples directory of your installation. So it's this MATMUL folder that I have just copied to a folder for the session today. You also have some examples for the different checks that are supported, as well as for the configuration file that we will be also seeing briefly later. So you have some documentation here that you should take a look, and also on the docs folder. So let me switch to the session folder for the MATMUL. So what we have here, you can see also on the right, is the main file, which provides you with an example code that will measure the time it takes for a matrix multiplication computation to perform. So the matrix computation is really simple, and this is the hotspot of the code. Like I was saying before, this is what we want to work on. And we also have some include files. This matrix.c is our include file over here, and we will be using that to show how you need to add compile flags. So essentially what you would do is invoke pw report, and we will be using that for our source folder. And you can see that invoking PW report for the main.c file reports some error. In this case, like I was already hinting, that the matrix could not be found. And in this case, what you need to do is to use GCC and clang compile syntax to provide the location of the include files. So once we do that, let me change to the evaluation analysis, which is the new default. Once you provide those flags, the analysis succeeds and will provide you this very brief table of how the analysis went. So this is very important for some people to already get an idea of what analyzer can do for you. So this is the idea of this report. And then we have this classification into the different kinds of performance optimization categories that I also introduced before. And like I said, you are offered suggestions on how to proceed next. So what you would do in this case is run the actions report. I will make this slightly smaller. Let me know if that's too small. So running the actions report, which is the main report that you will be working on, provides you with this report that follows the same structure of your code. So you have here two loops in the MATMUL function. This first two loop, which is the initialization, and the second one, which is the accumulation. And you see that, for instance, for the first loop, you already have that it is a vectorization opportunity. It's quite simple code. It is just initialization of the matrix to zeros. And then in the second loop, you have different issues. So for instance, you have some non-consecutive array access that is pointed out to you in case that you can do something about that. It will improve performance by means of data locality. You also have some array not being accessed in row major order, and then a couple of multi-threading opportunities here, which is really interesting. Let me point out that this, what I'm doing now, which is a Quickstart, is also available as a README file. That again, this example comes with Analyzer, so you can use it, copy and check it out for you with your installation. So this is what we were just seeing, so that the error and how to fix it, and then this report that you have over here, and it covers the different outputs. So what it's telling you here is that besides the actions report that I introduced to you, then you have a code coverage that is telling you how good the analysis went. So in this case, the whole source file was analyzed 100%, and half the functions were successfully analyzed, and over 80% of the loops. So again, static code analysis is tricky, and you always need to get this measurement of how good the analysis went, because it's very hard to get it to 100%. And in many cases, for instance, your code can call third-party software where your code is not available, and this, of course, cannot be analyzed if the code is not available. So we can follow this suggestion over here to increase the level of detail. So if we use level 2, what you have is that now your report is larger, you have more information, but you also have some clear suggestions for each of the items on what you can do next. So you can perform some parallelization. So that's what I will do next, just to give you a quick idea of what's there. Let me first show you PW loops tool, which you saw in the slide before. Yeah.
Sorry, just a quick question, just to make sure, because I remember asking this a while ago, but for this recognition of, like this could be a parallel for, can it handle classes? If there's an operator overload, you can obviously have multiplication for classes in C++. It'll still suggest it because it could be a pattern that could be optimized, but it can't be certain. So it would still recognize that pattern if the things are just classes?
Depends on the complexity of the code. So classes can be a little bit tricky, and C++ support is quite a fun endeavor. So mostly we support C-like, C++ syntax, but we would have to look into the exact code to be sure of that.
Thanks.
Okay, any other questions? Okay, so yeah, I was just trying to highlight here that, okay, for this particular loop, and you can always use this syntax, which is a file, a function, and then code location, file, and column. So in this case, we are focusing on this loop on 9, 15, so this loop over here. And we are providing this filter, so there is only one loop output by PW loops, and it will tell you that it's a multi-threading of loading opportunity and that it can be automatically parallelized using PW directives. So this is what the X here stands for. So going back to the previous invocation of PW report, you actually have this line here that is telling you that you can use PW directives to generate the directives for it. In this case, it exemplifies using OpenMP. So this is what I will do now. So if we run this, we will perform in place editing. So we will change the original file, and we should be seeing here on the right on the code editor the changes. So that's exactly what happens. It tells you that there was a for all for the C variable, and this region was parallelized using parallel for. So here you have the parallel section and then the for. So we have just edited the code. So if I run this, I should have run the baseline first, but I will do that in just a second. So running this multi-threaded version that we brought using PW directives, it takes less than 1 second, 3 seconds, less than 3 seconds. Sorry. So if I undo the code here on the code editor and run again, so we have the original sequential code again. So this should take slightly longer. So again, you can check all this information here on the README, as well as some information on other steps that you can follow next, such as learning how to use the configuration file, how to filter using different flags, and so on. So you see that it was over 28 seconds. So this was 10x speed up, pretty nice in this matrix multiplication example. Okay, any questions regarding this quick start of using analyzer with matrix multiplication? Otherwise, I will move to the demo of using the Canny edge detection.
I didn't see any questions coming in the chat, but just yeah, an opportunity to ask questions now. Please use the chat option or unmute yourself and ask the question directly. Okay, if not, I think we can continue, Javier.
Okay, great. So I will be moving to this code example here. Again, let me hold it on the right. And as I introduced before, this is the Canny edge detection algorithm. What it performs essentially is for an input image, it will create another image with the edge highlighted. Okay, so it's an edge detector. It is just one single C file, slightly over 100 lines of code. And our hotspot, we know from profiling that is the Gaussian smooth function. So it's this function over here, which essentially performs a blur in the X direction and another in the Y direction. So these two 3-level nested loops are what essentially compose this function, Gaussian smooth function, and it's the hotspot. So again, if we analyze the Canny.c file with the evaluation report, you will see that we have over 100 actions divided into different categories. Okay, so we run again the actions report to get the structure report with the different actionable insights. And you see that even if this is not the level 2, so this is just one line per each of the items, this is a lot of information. Okay, so what we suggest always is that you use a function filter. So we know the hotspot, so just let's focus on that. And we provide the function name using the syntax. And now we have the actions report just for that one function. So again, you see that we follow the same structure of the source code, the first 3-level nesting, and then the second one. And for each one of them, you have different recommendations regarding that variables can be declared in the innermost possible scope, which is always a good practice. And we have different opportunities for SIMD, multi-threading, and offloading. But I want to use this demo to showcase a hybrid parallelization that you can also perform. So let's dig deeper into this by adding a level 2 flag. So we increase the level of detail, so more verbosity, but also you have more interesting information. So for instance, for the opportunities, you get the compute patterns that were classified, and you get a couple of invocation of the tools to dig deeper by using PW loops or by using PW directives. So again, let me take the chance to just switch real quick to PW loops and provide you with some more in-depth. Sorry. So one of the nice things about PW loops is it also follows this hierarchical report that you will see which loops are nested inside which ones. And here you have again the different types of opportunities and classification patterns that we provide. But scrolling back up, what I want you to see is that you can use PW directives to generate hybrid parallelizations. And you can do that following this suggestion here that will tell you that you can apply multi-threading for the outer loop and SIMD vectorization for the inner loop at the same time. So we can just copy and paste this invocation over here, and you will notice that the syntax changes, and this is what is specifying the hybrid approach of multi-threading and SIMD at once. So if I run this, you see on the right that the code was updated, and the proper multi-threading directives were added in the outer loop, and then a SIMD clause, a SIMD directive was also added for the innermost loop, in this case with a reduction clause for the dotted sum variables, since it's doing a scalar reduction with the sum operator for these variables. So we could perform the same for this loop on line 847. We have the recommendation on top, but I will just apply that directly if I can find the proper loop. So in this case, I just added the multi-threading for the innermost loop, which is not what I wanted to do. So let me scroll back up, or let's run again the tool and see if we find actions. Again, focus on, well, if I stop having typos, sorry. Okay, so what we are looking is for the second loop to have multi-threading and SIMD vectorization with same thing. Well, it should be reporting for the second one. Must be some kind of bug in the code here. Well, I need to look into it. In any case, what I wanted to highlight is this hybrid approach where you have both loops in just one single invocation. So we are not confined to just a single parallelization type, and we can mix, such as in this case, multi-threading and SIMD at once. So this covers the essential uses of how you can invoke Parallelware Analyzer to get actions from your code, see how you can get suggestions on what to do next, how to act on those recommendations, on those remarks. How to use very briefly PW loops. There are many analyses in PW loops, and I suggest that you investigate them. So here you have memory accesses and memory footprint. You have flops analysis that will provide you the arithmetic intensity of your code, data scoping that is the more detailed regarding the data patterns that are in your code, and other analysis. So this, we don't have to cover this. We don't have time to cover all this, but I will suggest that you take a look into that. Okay, so I will just show you one of the, like I said, you have documentation in the with the tool, and you have this README that will point you to different investigation areas, such as the configuration file. But allow me to at least introduce you to the use of CMake. Okay, like you saw in the example before, so we needed to add some flag for this to succeed, right? The compile flag. So in this case, it was this flag. So in some code projects, it might not be feasible to use this syntax, this compile line syntax to add the flags. So we support using compile commands JSON database file. So I don't know if you're familiar with this, but I will exemplify how to create this using CMake. So we have this very simple CMake project, and this is the only line that's required, that you set this CMake export compile commands to on. You can also do that in the command line just when invoking CMake, just like by doing this. Okay. And if your project is not using CMake, but it is using Makefile, you can also use this with tools that will generate these compile commands from a Makefile, such as Bear. So that's 99% of the codes we encounter. We can either use one of these solutions to generate this file. So using CMake, if I have this CMake list project file, if I generate this or invoke CMake in this way, so this is not building the code, it's just creating the build files, and you can see here what it was created. What we are interested in is this compile commands file. So what you can see, if you are not familiarized with this, is it has an entry for each one of the different files that must be compiled with the whole command, including the compile flag. And this is what we will be using from this. So you can take advantage of this by using, for instance, config. We pass that file, and then we analyze the folder. And you see that the analysis succeeds again, because it's extracting the compiler flags from these entries over here. So when it has to analyze the main file, it will extract the relevant flags from here. And this is very, very useful for large code bases. For instance, before you were talking about GROMACS, that's one of the codes that we have, that we internally use for benchmarking. And we use this method. So we just generate the build files, not build the code itself, but just the build files. And one of those files is this compile commands. And then we use that in our analysis to extract the configuration files. Haven't tried this. I think here you have a Makefile. And we can also use the Bear tool to extract the configuration, the compile commands file. Something failed in this case, like I said, I hadn't tried that, but I don't know if I have a build target. Okay. Yeah, not sure exactly what's going on, but again, Bear is a very useful alternative for Makefiles. And like I said, with this we cover like 99% of the code, and this is a very, very useful option to have and get rid of all those inconvenient compile flags. Okay, so yeah, we don't have much time to go into more details. Again, this was just a quick introduction, see some examples of how to parallelize using Analyzer, but there are many other analyses, so I would suggest that you go ahead, try the tool, reach out to us if you need any help or extension of the trial or whatever. We are happy to help and receive feedback. So for feedback we go, if you have some questions, just fire away.
Thank you so much, Javier. And there were some questions in the chat, so let me go through it. Just 1 second. So at some point, Alexis was asking about the hotspot. Was the hotspot identified with previous profiling? And I think it was closer to the when you have started to work with the Canny example. But yeah, maybe Alexis, you want to clarify?
Well, I think that's if I got it right, that's a common question. And no, we do not do profiling at this point. I should have been clear about that. That's something that I usually emphasize. We are not trying to cover what profilers do. They already do that very good. So the idea is that you use your favorite profiler, gather the information about which one is your hotspot. Actually, that's normally some kind of dynamic analysis. And then with that knowledge, you use Parallelware Analyzer to focus on those hotspots. But you should be using some external tool. So for instance, here real quick, regarding vectorization. So you were saying one of the optimizations that the compilers do is automatic vectorization. So in this case, with the PWLoops vector support, you will have a report that again is the same structure that we were seeing before in the code, these 3-level nested loops. and it will invoke the compilers available in your system. At this moment, CLAN, GCC, and Intel ICC are supported, and will request the vectorization reports and tell you which loops can be automatically vectorized by each compiler. So, and if it cannot, in this case, GCC cannot automatically vectorize any of these loops, which is the reason. Okay, and get an overall overview of the results for auto-vectorization by each compiler for each loop. So this is pretty interesting. You have here, for instance, the reasons. So GCC is not able to vectorize due to the loop being an outer loop, or because of some complex control flow. Okay, and in this case, only this one loop is automatically vectorized, and only by CLAN. So this kind of optimizations we are taking into account, of course, vectorization, that's very core to us. Then other specific, more advanced flags, more to the point of your question, sorry, I digress a little bit. So other more advanced optimization flags, it will depend on a case per case basis. I mean, we are not able to support each of the compilers and all of the flags. That's very, very big task. But some of the optimizations on, for instance, the target architectures, especially in the case of vectorization, we do take into account. So hopefully that replies. Okay. Okay, thank you.
Thanks, Javier. This is really cool. I mean, because reading the vectorization reports from different compilers is kind of complicated from the user perspective, because they usually use very different formats. But yeah, having such a summary is really, really cool.
And indeed, here you can even get the messages from the vectorization. So we try to filter and digest that information for you and try to make it simpler, because it's like you said, it's really complex. You even get the invocations here that you can use to get the message yourselves.
Exactly. Thanks, Javier, for joining us in such early hours in Spain.
Thank you for the opportunity and the time and attention. Thank you, everyone.